Okay, have you checked? Right? So, equation of state basically, what is it? The dependence, it is basically the dependence of pressure on other parameters like density, like temperature. For ideal gas, we know the dependence, it is P proportional to rho into T. For degenerate matter, there is no dependence on temperature, only dependence on density. Now, we will consider this class of objects right now. Let us consider those types of stars where such equation of state are observed. That means pressure is equal to some constant K. There may be many things, many constants inside. It doesn't matter. Pressure is equal to some constant A into rho to the power gamma. Now, if there is a star out there, we do know there are stars out there which has this form of equation of state, then we will call them polytropic star. Okay? Now, you see this gamma, it can be related to another index n known as polytropic index n. So, this is the relation. Okay? Now, you see. Let us look into a little bit the mathematics of this polytropic star. You see, let us start with the equation of hydrostatic equilibrium, this equation, and from there it is possible to get down this another form, a different form yet of the hydrostatic equilibrium equation. In fact, this form you can also get in fluid dynamics as well. It is also possible to get it from there. Now, let us introduce two different, now we are going to do a change of variables. Let us introduce an independent variable xi and a dependent variable theta through these relations. So, now we are going to change this. From density and radius, we are going to theta and xi. And as a result, we get this relationship. What is this alpha? Alpha is this, and n and gamma relation is over there. And after some mathematics, you can check in that video on Polytropes. I have done the entire mathematics over there. You can check that this equation, it gets reduced to this form, a very compact form, and this is known as Lane-Emden equation. Okay. Now, of course, this equation has to be solved, taking into account the appropriate boundary conditions at the surface, at the center, right? Now, what I want to emphasize at this point in this class is that as a result of this calculations, it can be shown that there is a, you will see, there are a lot of detailed equations are there for this central density, and also expression for mass and expression for radius. You will find it. There are lots of expressions. Now I am not going to the details. What I want to emphasize right now, basically I want to talk about both white dwarf and neutron star together, and this is what I am doing. You see, from this all mathematics, you will get this relation, m proportional to r to the power some function of n. Okay. So let us now stop over there and let us now move to this part. You see, where have we seen such a relationship? We have seen for white dwarfs, remember? Or basically, not just white dwarf. We have seen this relation for degenerate fermionic system which is self-gravitating. Degenerate fermionic system which is self-gravitating. Now there are two such possibilities. One is when we have electrons providing the degenerate pressure, and another is when we have neutrons providing the degeneracy pressure. So one object is white dwarf, another object is neutron star. But in both of these cases, we have this identical scenario. For non-relativistic case, pressure, we have worked this out, right? Non-relativistic case, the pressure depends on rho to the power 5 by 3, which means you can work it down from there. N is equal to 3 by 2. And for relativistic, ultra-relativistic case, we have pressure proportional to rho to the power 4 by 3. That means n is equal to 3. Right? So this we already know. We have done this. For neutron stars, in this entire expression, you just put the fermionic mass to equal to neutron mass. For electron gas, you put the fermionic mass equal to the electron mass. That's it. Nothing changes. Okay, this is how we approach the problem. Now let's see over that part. So we have this expression, mass and radius relationship, right? Now let us see for n is equal to 3 case. That means the non-relativistic case. So you see, for this n is equal to 3 non-relativistic case, if you put it down over here, you will see this relation. M is proportional to 1 by r cube. And this is the famous mass radius relation of white dwarf that we have worked out, but in a different way. You check your copies. We have already obtained this thing, but using a different approach. Right now I am using a polytropic approach, a much more generalized approach. Now what about the other case, the relativistic case? You see, if we put n is equal to 3, you will see that m becomes independent of r. What does this mean? This means that now m becomes constant. So this means, you remember the maximum mass of white dwarf, the Chandrasekhar mass limit, it is the same old thing. So there you will get an idea that the mass becomes constant for the ultra-relativistic fermions if we consider a degenerate fermionic self-gravitating system. So this thing is basically Chandrasekhar limit for white dwarfs. Similarly, we can get the same limit of maximum mass of neutron stars. Same thing. Just like that we did for Chandrasekhar mass, white dwarfs, and obtained the Chandrasekhar limit, right? But remember, till now everything was fine. But now there are certain differences between white dwarf and neutron star. Number one, this mass radius relation, it is still okay for neutron star. Why? Because we are considering non-relativistic particles. Okay, but the moment I am talking about the relativistic neutrons in the neutron star, then you already know that for relativistic neutrons, the general relativistic effects are very important. We have to take that into account. So, this mass limit that you will get as an application, as a result of application of this concept for neutron star, will not be correct. So the first correction will be due to general relativistic effects, which we have discussed. Why? How general relativistic effects are important for neutron stars, but they are not so for white dwarfs. This we have discussed. Now there is yet another important effect that we have ignored. What is it? You remember, in the neutron star, basically we were having neutronization, protons being converted to neutrons by inverse beta decay and all that and all stuff, right? So, if the neutrons they come very close to each other, what will happen? You see, between electrons there was this Coulomb interaction, which we know about. And in fact, in the equation of state for fermionic matter, there is also a correction due to Coulomb interaction that I have not discussed with you, but it is there. So similarly, if we are considering neutrons now, are they non-interacting? Of course not. Neutrons, they interact by nuclear force, strong interaction. So what about the strong interaction? We have not talked about it at all, because it is also there, but till now neutrons were not coming in close enough. But if they come very close to each other, then strong interaction, the nuclear force will come into play, and we will have modification due to this nuclear interaction. In fact, it is hoped that observations of neutron star will help us to get some information about the nuclear force itself and help us in nuclear physics. Why? Because still as of today we do not know. The information about nuclear force is very poorly known. So in fact, this is one of the reasons for the uncertainty in estimating a lot of properties of concerning the neutron stars. I am right now talking about the maximum mass of neutron star. So there are two problems associated. One that we have not discussed is general relativistic effects here. Another, we have not discussed the effect due to nuclear interaction. Now, in spite of all this, let us think for a time being that let us forget these two effects for the time being. Then it is still possible to get an estimate, and the estimate gives me the maximum mass of neutron star around 1.4 solar masses or so. And what does observations say? If you look into the observations, you will see that there are approximately 70 neutron stars having mass in that range, little bit lower than, and in very few cases the neutron stars have masses of the order of 2 solar masses. So this means that most of the time this is there, but there are certain scenarios where the neutron mass is exceeding this limit. So this means that the effects of the relativistic and the nuclear interactions will be very important. But again, our observations are limited by our technological advancements, right? Maybe 200 or 300 years from now, we will be able to observe more and more neutron stars. And then we will be able to understand more of this nuclear stuff as well. Nuclear. Experimentally. Any questions? So this is an overall discussion taking into account together the white dwarf and the neutron star. Okay? Yes, one thing I forgot to mention is that, so here we have talked about both white dwarf and neutron star together, fine. Now you see, here we have talked about this non-relativistic hydrostatic equation. Now similarly, we can also have a relativistic hydrostatic equation, just we have talked about it, that is the TOV equation, right? And from the TOV equation, if we consider the constant density model, we will get a neutron star model. From there, you remember, we observe this. So, from the TOV equation, for constant density model, we observe that there is, for finite central pressure, that means pressure at R is equal to 0, we will get this relation. M by R is less than 4 by 9. So we get a constraint. Right. Now this is a neutron star model. Remember, constant density model. Okay. And yet another neutron star model here is using this relation. Polytropic model. Here we are getting. So this one I am talking about. So in this blackboard you are right now seeing two very different models of neutron star. One is using just the TOV equation, constant density, and another is using the polytropic form. When the neutrons do not become, when the neutrons are still non-relativistic. So in this board we have talked about two neutron star models as well. And for white dwarfs we have already discussed this before.